Now we want to apply the second derivative test. This test tells us if we're given a function, the first derivative is equal to 0 and the second derivative exists, then if the second derivative is greater than 0, we're going to have a relative minimum. Whereas if the second derivative is less than 0, we have a relative maximum. Finally, if the second derivative equals 0, the test fails and we have absolutely no information. Let's apply this and some previous ideas to the function f of x given here, 2x to the third minus 3x squared minus 12x plus 5. First, let's take the first derivative, which will give us 6x squared minus 6x minus 12. If we take out a common factor of 6, we're left with 6 times x squared minus x minus 2. If we continue to factor this, we have x minus 2 and x plus 1. So our critical numbers then will in fact be x equals 2 and x equals negative 1. Let's take those 2 points and take the second derivative and see what happens if we substitute them in. Take the second derivative here, we get 12x minus 6. So if we first put in 2, 12 times 2 minus 6 gives us 24 minus 6, which is greater than 0. Now the fact that this is greater than 0 tells us that when x equals 2, and since the second derivative is greater than 0, we're going to have a relative minimum. So at x equal 2 we have a relative minimum. I've selected some x coordinates already and found the y values, so this will be a relative minimum here. Let's take the other critical point, x equal negative 1, in which case we wind up with 12 times negative 1 minus 6 gives us negative 18, which is less than 0. So that tells us when x equals negative 1, we're going to have a relative maximum. So if we look at x equal negative 1, here we're going to have a relative maximum. Please notice also that x equal 2 is a critical number, and we have a horizontal tangent there. X equal negative 1, we have a horizontal tangent there. One last piece of information, let's see if we can find the point of inflection. We take 12x minus 6, set it equals 0, 12x equals 6, so x equals 1/2 will be in fact our point of inflection where the concavity changes. Let's see if we can sketch a graph. X equal to 1/2 is important in that the concavity changes, so up until we get to 1/2 we're spilling water, but once we get at that point we're going to be holding water. So this would be the resulting graph from the information we've learned from our second derivative test.